Welcome again to the Applied Topology seminar. The speaker today is Shmuel Weinberger, and he will tell us about his latest obsession, geometry and topology of decision.
Great. Welcome, everybody. It's a real pleasure. I kind of regret that I can't, offer you all some coffee to share with me. Let me helplessly or hopelessly, let me plug this journal, the Journal of Applied and Computational, that I hope work to. Currently, the backlog is pretty short, so we're always really on the lookout for. Anyway, so yeah, I think that every days with issues of governance and decision making, and they come up in a lot of different places. And what I want to talk about is well, since I'm a topologist, I have to think about it through the lens of geometry and topology. So what I want, start off easy and show that there are geometric aspects to these kind of questions. I'll move more in the tradition theorems that these are kind of there's a well-known theorem of arrow that if you have to pick a slate of pen. I didn't hear your question, Henry.
Yeah, so we're having network issues where the video and audio is spotty for everybody. So I'm going to ask everybody to turn off their video. We'll see if that improves it. Hopefully that's just a bandwidth issue and not a connectivity issue coming from your end, Shmuel, but we'll see.
Okay.
So can everyone try to turn off their own video except for Shmuel, and we'll see if it gets better.
For now, okay. Talking to the set of you. I do hope I get some feedback in this direction, or who knows which way things will go. So, yeah. So let's see. So there are various cases where you have, say, multiple people.
Something like my only concern is that the sparsity cannot produce any localization. To the best of my knowledge, the only thing that can do, to the best of his knowledge.
Hello?
Sorry about that, Shmuel. That was sort of a negligent user who was unmuted when they shouldn't have been. So.
Oh, okay.
We're off to a bumpy start, but I think we're ready to begin now. The video connection is good too.
All right. No, this is raising all haven't thought about before. Okay. So anyway, so I'm imagining that I have like two people who are, say, giving me advice. One gives me the number 8, the other tells me the number 10. Okay. Or, well, that's one interpretation, right? One is yelling 8, the other is yelling 10, right? So of course, we're geometers, thing on the line, and here we have a 10. And the question is, what should we do? So when there are just two people and think that there is some kind of conventional wisdom to pick the average. Okay. So now let's think about what the meaning of that in different settings, and question how principled it is, and also what happens when we generalize this to more than, suppose I have a third person here who would be telling me 9.5. Okay, what happens if if n is the number of voters or advisors? Okay, these are okay, and and what we're wanting to do is we want to aggregate. Okay, so. And I began thinking about these questions in earnest, actually, right before I became chairman at Chicago, which was a long time ago. And so let me talk. There are countless committees And at these committees, various people will, suggest policies, will say yes or no, so on and so forth. And my first effort, when I first began thinking about it, let's consider the situation of an advisory committee. Okay, it doesn't decide anything. Its role, right? It's supposed to give you, and then when you aggregate it, right, the role of the aggregator is to make the right decision. Okay, so now in this case, so I was thinking along these lines, and I was thinking, oh, well, so one thing that you could do, of course, when you have a situation like that, is that then you would take everyone's advice and you average it, right? But, and that seems really fair, okay? But at the moment, I'm not, right, this is an advisory committee. This isn't a committee that's actually making the decisions, okay? So I realize that the role isn't to be fair to all the people on the committee, right? The goal is to make the right decision. So I said, great, I've already been in this department more than 20 years. I know everybody's track record. I've seen how they voted on all sorts of things, and I know, based on later events, by the way, I am a person who's capable of admitting when I'm wrong, so I really can see later events, and I try not to say that someone is right if and only if they agree with me. But anyway, so for each person, I had some feeling about how often they were right. What I wanted to therefore do was give each of them a weight. And that would decide how much I would weight their decision. Okay, so let's just imagine that they were deciding between 1 and -1, just deciding two things. What I quickly discovered was the ith person by this quantity, log of pi over 1 minus pi. So pi is the probability that this person is right. Okay, so if this person would be right all of the time, right, that person would get infinite weight, and of course that makes a lot of sense, right? I'm just going to listen to that one advisor, right? There's no reason to listen to anyone else's, okay? On the other hand, if the person is wrong all the time, they are a fantastic person to have in the meeting, right? Because you go ahead, you listen to their advice, and then you do the exact opposite, right? They get the weight of minus infinity by virtue of their PR. Okay, this is right. So this is, and one of the assumptions for this method, by the way, this is a practical method. It's more or less the idea behind add a boost, right? People don't usually use this on committees with people, but they use things like this when you have a whole bunch of machine learning algorithms that are based on different principles, and you're getting different advice from different ones. And what you want to just do is combine all of them to get an answer. So you don't go ahead and have any kind of notions of justice. You instead go ahead and you look at track record and you decide how to weight them. Usually all of these things are better than chance, right? Their PIs are bigger than a half, so they get bigger weights. Now, one of the problems that I had two problems in implementing this in my department. Well, firstly, no one in my department would have known if I implemented it, right? Because this was advisory. I didn't go ahead and tell Mr. X, oh, you happen to have a negative weight. Okay, that wasn't it wasn't exactly that kind of problem that would have arisen. I'm trying to think So there were two problems. One of which was that for this to be correct, you really need the various members of the department to be independent of each other. Right? If you have guys that are correlated, then you quickly see that this is a ridiculous method, right? Because if I have two guys with the same P and I count them twice, then I'm just going to be overweighting that person, right? There's no advantage to when people talk to each other. So actually, my solution to that was, so therefore people should just debate. We should get rid of debate so that people can't influence each other. I just want to have people's gut reactions. Well, that didn't work. why it seems that might be the method for various judiciary. But anyway, right. It does make us wonder about in the jury system where you have a system where you have people arguing it out to try to get to consensus. That you vitiate the advantages that one has numbers, right? The basic idea, of course, would be that if the PIs are bigger than a half, then the law of large numbers will tell you that the majority view is going to be working or something like that. And that this beyond that. Okay. Anyway, the other reason why I couldn't do this is, say, when I wanted to apply to a department meeting to decide which of, say, two candidates to hire, it turns out that the university statutorily insists that each person's vote has to be counted equally, and that there are ideas of fairness. And again, depending on your application, the question of fairness, has a different role. So like when we have voters in an election, you could talk about fairness among the candidates, about whether each candidate is being treated fairly. I think that at the moment, we're not worrying about that aspect, although in jury trials, again, that aspect is very important. That we're worried about the fairness among the various people who are trying to influence the outcome. Okay? So for some principles, we want to be counting it. We want to go ahead and, so let me at the moment focus on fair ones. Okay, although one might argue that that fair decision process, are very, very limited application. As when we're going to want to do aggregation, it might be much more like we want to get the right answer. Various people are giving us advice. Okay, you might have some engineering device, you might have some device, and you have various instruments that are doing measurements in different places, and you're trying to, combine the information from various sources. Okay, every application has a different aspect to it. Okay, so let's see. So, one kind of method that people have is there's sort of a collection of methods that are sort of either based on negotiation or markets, etc. Just versus, a centralized aggregator. Okay. I want to keep this distinction in mind. As we go on. Okay. So anyway, now I suppose I have a bunch of people and they're giving me things on the real line, and the question is, what would we get to? So suppose now I'm going to imagine that I have a whole bunch of people. Okay, and we're going to do it by vote. Okay. So here I have 7 and 6. Okay, over here I have, say, 50. Okay, so here we have, right? So here we have, what are the interpretations? You could make up your own mind, right? This might be choice. You might imagine that there are candidates whose spectrum go from left to right. Okay, and that people will vote for the candidate whose position is closer to their ideal position as described on the real line. Okay, some very, very simple one-dimensional model. Okay, so in a situation like this, so when you're on the real line, things are quite simple. And let's just think, suppose I have two candidates. Okay, so I have a blue candidate here. Okay, and here I have, say, a red candidate. Okay, so for these two candidates, so this red candidate, I believe, will be chosen by this guy and that guy. And this one well, it's not clear. This guy is somewhat in the middle, so we don't know. I should have brought a picture, a little bit clearer. I apologize. Let me pick another candidate. So I pick a candidate over there, right? So let's forget about the blue guy, right? Okay, so all three of these will pick that guy, and these two pick the red guy. Now, what happens if I now say, okay, this left wing one, if I put one further out here, right? If I go very far left, then someone in the middle they'll begin moving towards the right wing. Okay? And if you think about it, if you have a whole bunch of candidates, what tends to happen is, does everyone see what's going to happen, by the way? I don't know. Oh, everyone's muted, so I'm not going to know. And no one is going to wave since everybody is invisible.
No, we're following you.
Okay, good. What happens by voting, if you just would do naive voting, the output would be basically the median. Okay? So, you see, as I move my candidate, past the midpoint between two voters, right? Those are really the key points, the midpoints between the voters. As I move, then as I pass that midpoint, someone will then shift. Okay, and if we're going to be doing it straight by majority rule, what happens is, if you have, say, an odd number, then there will be exactly one median, and that will be the point. That will be, in some sense, the ideal candidate. Any other candidate would get, in a theoretical election, fewer votes. Okay, and again, right, this is a really dumb model because everyone is voting, people are voting rationally, there's no strategic voting, etc. Everything is happening one at a time, and more or less, there's nothing much that could happen in this kind of vote. There's nothing exciting. It's hard to manipulate this election. Suppose that I go ahead and I try to first make the decision between A and B, and then B and C, and then C and D. It's always clear which is the one that's going to be chosen. The one that is closest to the median, where closest is defined in this abstract metric, right? The one that's based just on, midpoints of this, the ordering of the real line together with the midpoints. So for situations where things are real valued, okay, the median is actually a very intelligent, fair solution. It obviously doesn't depend on who votes things. It doesn't matter which order the candidate, unless there's some rule about what happens when it's a tie, right? If you're going to have, if you're not going to have the median actually being a viable candidate for some reason, and, you can imagine that there are some circumstances, but pretty much it's what happens in the case of voting on the real line is, incredibly straightforward, very robust, okay? I want to point out, though, of course, that the median, right, this ignored all metric structure, right? If in other words, if I take C from R to R, homeomorphism, okay, more or less what I'm going to obtain doesn't change very much, right? It's just going to be, in this case I actually, right, in this case I have an odd number. If I have an odd number, then literally I'm always going to be getting exactly phi of the result of the previous election. Okay, if I have an even number, then there's some small interval of change. I'm always going to be lying with an interval. That's going to be, so to speak, the feasible outcomes of this aggregation problem. Okay? In a simple universe, a lot of politics does seem to take place on a real line. And that is why some people argue that some voting paradoxes, etc., are not as awful as they might seem. In other situations, by the way, the use of the real line, this is, of course, economists constantly try to introduce utility functions. And what they want to ultimately do is, well, okay, never mind. I don't want to, let me not talk about that at this point. Okay. Yeah. So I want to show you a picture that I learned from Don Sari, who's written a lot about using dynamics and geometry in economics problems and aggregation problems. And what I want to do is just imagine the same situation, but now my voters, instead of choosing someone who they like best on the real line, suppose that they care about more than one thing, right? You care about research and teaching, okay? Okay, right? There's more than one thing that's entering your decision, okay? And my axioms are that a voter will always vote for the candidate that is closest to their views. Okay, and closest I'm going to be using the Euclidean metric. Okay. All right, so what happens here? I found this fascinating, as an incoming chair. And I think that this is sort of worth everybody observing. So let's just do a case. So I'm going to imagine that I have 3 voters, okay, denoted by these points, okay? That this is voter A, B, and C. Okay, and let's imagine that we have, okay, now I'm going to describe for you an evil chairman, okay, who, let's say the chairman does not get a vote. He is not one of the voters, okay, right? So what he does is, so the department is trying to decide, say, what should they do, right? Should they go after, say, let me use, okay, so there is some possible candidate that the department might like. And everyone goes ahead and says, oh, this is a pretty good person. We understand that this is, that all goes well. But now the chairman, being the kind of evil guy that he is, looks at this guy and says, the chairman, for some obscure reason, really likes someone out there. Okay? Okay? And what I want to do is here, I want to just point out what could happen. What happens if I take this line, okay, right, the line from A to B, and now if I just flip over I will get a new candidate for whom A and B are indifferent. Okay, so being the clever guy that I am, I don't know when it switched from being me. I never I'm about to describe, but okay. If I go ahead and I take the flip across this line, okay, and I then move just a smidgen, right? A smidgen is a technical word like 1 Planck length. Okay, I move a smidgen closer. What I will do is I will now have a new candidate, right? Right? So let me just draw. This is the original triangle, right? This is the original triangle that you would somehow feel that's sort of like the median, one would imagine. Okay, but here by having arranged this thing as being a sequence of elections, I now have this person. C is, of course, disastrously unhappy. Okay, because I've made things much, much worse for C as a result of this flip. But A and B are now both happier, and it being a democracy, we do the will of the majority. But then I'm a really good chairman, and I'm never done. And I then say, okay, yes, it's definitely, we now have a better candidate than our first one, but I have another idea. And what I now decide to do is flip with respect to BC. Okay. Okay, so there, that would be the flip. B and C would be indifferent to this change, so then I will move a smidgen earlier. Again, a Planck length, something very small. B and C now vote. C feels better because now C has a positive vote. B is thrilled. B's will was followed twice, and now it goes further. And if you think about it, I can now, I just am constantly, where can I go in n steps? N steps of voting is equal to, n steps without really changing anything. Okay, so in other words, I imagine that you do this, and then, each step you'll have to move it, less than some epsilon, but something really insignificant. an infinitesimal motion. Okay, after n steps of voting, that's just sort of n flips over the edge of a triangle, right? So really what you're doing is you're looking at a triangle, and then you have three involutions of the triangle that you're flipping with respect to, and this generates a group. A group of motions of R2, and it's sort of fun to figure out what this group looks like. I mean, it has, but in any case, I mean, it's no great shock that this group contains translations in it. So, number of votes, I've gotten the ideal candidate being chosen to be way out there, translated very far. I mean, okay, and then in my last thing, I said, oh, this is just awful. Let me just remind you that we had this candidate over there, my brother-in-law, and I really think that, and all three agree that that's the better candidate. We finally have had an election where all three are in agreement, and that is what we do. Okay? Now, by the way, this has nothing to do with my talk, this example. It's just an example, firstly, of the fact that geometry makes a difference. As one thinks about these problems of aggregation, abstract principles like fairness, have some really, really concrete meaning. Doing the most naive thing about following majority rule has implications. Okay, so there's sort of a lot of general scientific principles that one can deduce from a model like this. It's also interesting to puzzle through this. And it immediately indicates to you that the people who have power in elections are not necessarily the voters. It might be those who set the agenda by deciding the order in which decisions are made, or by the possibility of indicating there was really no reason even at the very beginning to pay attention to that person, just because, somehow there might have been, the argument speaks for itself, but what it argues for, I think different people can make different decisions. Some have argued to me that what this story tells you is that A and B were already in a state of sin at the very beginning, because they were willing to screw C over the slightest advantage to their principles. I'm not sure that, that one actually solves the problem, because you could easily imagine that, remember, these are supposed to be, it could be that the reason, that where this thing is positioned in space, I'm supposed to be thinking, right? I mean, these are supposed to be various variables that I'm looking at, and one of the things I'm taking into account are what other people care about. Some people will also argue that this is an issue that really tells you that individual rationality is different than the rationality that's relevant for aggregates of people, right? Because it only happens when you have, 3 voters or something, and that if you only had one individual, but I'm not sure that that makes a difference. I easily could imagine circumstances where these 3 things are different processes in my brain that I think about as I'm trying to make a decision, right? And, if I care about enough things, then each of them will, so to speak, have a vote in terms of which decision I make. So in any case, for these kind of, I think that this is actually an important example to think about, just in terms of the mere fact that the geometry and topology of a space has some implications for voting and decision processes and so on. Okay, what I want to now do is move to a different kind of model. Okay, in a model like so. By the way, so all of this was based on doing these things serially and stuff like that. If I would be having a centralized aggregator, someone might tell me what I really should do is just look at arg_inf of some penalty of the choice, versus the voters. Okay, so let me just comment about what that would mean. Okay, you know, it is an intuitive thing, and it works quite well, you know, in some situations where things are adequately numerical. But I'm soon going to be moving towards nonlinear settings. I do that. Let me just slow.
Hey everyone, it looks like we lost Shmuel.
How do we reach him?
Voter.
It shows that he's... okay, now it's back.
And the choice made by society, or the aggregator, or the chairman, whatever you want, you know, however you would want to refer to it. Okay? I mean, this would be one method where you would choose the supreme. Okay? I mean, one might be you take the sum of these distances. Okay? A third choice might be you take the sum of the squares of the distances. Okay, right? All of these things, you know, we're trying to take into account, you know, we're assuming that everyone is going to be unhappy, but they're not going to be equally unhappy based on what's chosen, right? The only way they're going to be not unhappy is if, you know, their decision itself got chosen. Okay, so I mean, if you make these choices, this is the one, you know, this is the one that people always use. They don't know that, people aren't aware that they're always using it, and it feels funny, right? I mean, why is it that you would use the square of the distance? Okay, this one, what this suggests is when I have a whole bunch of different voters, this is the one that gives you the average. Okay, you know, whenever you're in a Hilbert space, that is the definition of the average. That's the principled. This is the principled explanation about what it is that you're doing, right? It's a least square minimization. Okay. Other ones, this is, you know, and it, you know, might remind people about questions about, say, you know, bottleneck distances versus a Wasserstein 2 distances in some other settings, but I don't want to go there. That's too specific an application. For this one, right, what's going on, okay? Right, let's look at our voters on the line. This one here, right, I mean, we're just going to be looking at the most unhappy person, okay? So what this one is sort of a cool thing. This is sometimes called the Cartan centroid.
And Shmuel, quick
yes?
question. You cut out for a moment. What does the first one say? It says the soup of all voters of the distance from the choice
distance
of the
between
voter.
the choice of the voter to the choice made by society.
I see.
Okay?
Thanks.
Okay, so if you think about it on the real line, okay, let me just point out to be. So on the real line, this aggregation, the max of the voters, you look at the min, and you take their average. Okay, in other words, we don't care at all about the run-of-the-mill voter. We only care about the extremes. Okay, now this is the one that seems to, you know, in my experience, little children love this one because they just say, well, if everyone, what you want to do is you want to minimize the amount of unhappiness that anyone has and that there are no trade-offs among people. Okay, this is sort of a, you know, straight Kantian perspective. Not that I'm saying that Kant was a child or anything like that, or that children are Kantian, but it's right where you can't sacrifice, right? I mean, it's a Pareto optimality. You can't sacrifice the utility of anyone. Right, you have to treat, you know, for the sake of someone else. No, you can't go ahead and say, oh, there are, you know, a few outliers that we ignore, and then we're going to just try to deal with the reasonable people. Okay, all of that stuff goes away. Okay, maybe that's one of the reasons why, except for, you know, some bottleneck distance situations, people will frequently avoid these kind of things. This one feels a little bit plausible. This feels like the kind of thing John Stuart Mill would have loved. Right? Everyone's utility counts the same. And when I lose one util and someone gains one util, we're entirely indifferent about that. Okay? And this is the one that will give you the median when you're in one dimension. Okay? Of course, we all know there are all sorts of great reasons why one ends up using this, but I don't think that they're sort of a priori moral arguments. There are practical arguments that this is extremely easy to compute. You could also go ahead and merge different data streams and combine them. If I use 2/3 of the voters to get one of them, and then I use 1/3 of the voters to get a different one, I know to take a weighted average between those two to be able to combine it. I mean, there are many, many advantages. And of course, since there are also those advantages, it's easier to prove theorems about them. So there's much, much more science behind this choice. But I think that if you just think at the level of naivete, I would say that, various moral and political philosophers over the years have made different choices about these. Scientifically, it's not always the case that one has to view all of these things equally. Okay. Anyway, so now what I want to do is I want to move to topology. Okay. And deal with a situation where no averaging is naively possible. Okay. Although I should point out that a lot of what I said about the real line and Euclidean space applies to all sorts of spaces of non-positive curvature, which do occur in various kinds of examples. Okay, so let's think about the following abstract model. So I have X is a space of choices. Okay, so this model was first introduced by Graciela Cicholnitsky many years ago. Okay, and I want to I'm not sure. This will be, sort of the space. Okay, I'm on a desert island. Okay, and the people living on the island have to build something, and they have to decide where they want to build it. Where do they want to put some, say, the hut where they store their food or something, right? So there are going to be various people choosing. They can't put it at the very middle of the island because there's a volcano. Okay, why is there a volcano? Because if there weren't a volcano, this island would have been contractible and I wouldn't have anything to say. Okay, it would be the convex case, right? So I have a space of choices, and then you have a whole bunch of voters. So let's say there are n voters. Okay, so now what do I have to do? Okay, what is necessary to be done? So I have this space X, I have n people making decisions. N equals 2 is already interesting. Okay, and I'll return a little bit to the case of n equals 2 after I make some remarks. Okay, so I have this, and now what I want to just do is we want to have some process. Okay, so now the first condition will be that A is continuous. Okay, I'm imagining that, right? So X is a space. I'm imagining, this one. Whenever you go ahead and you say something like this, you have to make up a story that goes along with it. So continuity, the story is that this is a form of rationality. Right? That if the voters each change their opinion only the slightest smidgen, right? It shouldn't result in some kind of really that the aggregator, as a result of this slight change in the opinion of the voters, they're each changing some choice by a millimeter, all of a sudden I'm going to go ahead and put it on the other side of the island. That sounds incredibly precarious, like I'm capricious. Okay, so we're going to assume continuity. This one, I think, the truth is that this one, in practice, is hard to believe in. But nevertheless, The next one is that A respects unanimity. So that means that if everybody votes the same way, that's what you do. Okay, now, in all voting situations that I'm aware of, this law held, with one exception. There was an ancient institution of the Sanhedrin that would, in situations of capital cases, if it was unanimously decided to convict someone, then they would acquit. Okay, so that's a failure of the unanimity axiom. In that case, by the way, the overriding philosophy was that if everyone was unanimous to convict, then people didn't really try hard enough to understand the case. No case should be that clear cut, right? I mean, so there was a different fairness issue. It was a matter of not the fairness to the various judges in the trial. It was an issue of fairness to the between the outcomes of convict or acquit. But in any case, this one I think people are pretty good with. Okay, the unanimity axiom, and then the last axiom is the one that is the one about fairness, which is that that's a of x1 x2 equals a of x2 x1. Okay. Or more generally, there's an action of the symmetric group. The symmetric group acts on x to the n, and I could imagine that I want to say that A composed with, some permutation of the coordinates of a vector should be what A of the same vector. Okay? So this is the one that is democracy. Right? That whenever we do, the votes, all the votes are put into a hat. Okay? This axiom could be weakened, but you don't need the whole symmetric group. But let's, for simplicity, we'll imagine the three axioms. Okay? And okay, so this is some kind of ideal situation, and of course, there's this whole, just like the arrow impossibility theorem, there's a theorem about this situation as well. Okay, and the main theorem, I'm looking at time, so I have to go a little bit faster. So the theorem is this. If A exists for a finite connected polyhedron. So by a finite polyhedron, I of course don't mean finitely many points. I mean a finite number of simplices. Then either n equals 1. That one is pretty easy. There's one voter. We do what he says. Okay, that one is pretty easy. Or X is contractible. Okay. So by the way, there's some exercises. It's worth verify this for X equal a circle. Okay, right? For that island, the island that I drew is an annulus, circle across an interval. If you think about it, there are therefore two different directions. There's a circle direction and an interval direction. And the interval direction, we could just average. There's no problem about aggregation, for those set of preferences. But it's for the circle that we run into a problem. Okay? And for any, for n equals 2, this is exactly equivalent to the statement that a Mobius strip doesn't contract to the boundary circle. Okay? So, but it's true, but as an exercise for the case of a circle, it's not so hard. So anyway, so that's one exercise. Another exercise is you might want to check that if X is contract or convex, then you would know what you would do. You would just take the averages. So if X is contractible, then there exists an aggregation method. Okay, so contractibility is a good topological analog. Okay, but this is already an interesting feature. Here's another one for those who like this kind of thing. If X is the projective space in a Hilbert, if we want to space, then an odd number of people can aggregate. Okay? This is really a theorem about finite dimensional compact polyhedra. Okay? There are examples of infinite complexes that are either finite dimensional, or like this, where you could have aggregation. There are even two-dimensional spaces where you could aggregate for any number of people. Okay? And those have interesting interpretations in terms of what go on such elections. But I, again, look that I'm going to go there. But anyway, so it's not the case that you never can do it, but for, sort of what many people will view as the natural finite dimensional versions of this, you certainly can. Okay, so let me just compare this. Okay, and by the way, two people could do it for those who know what this is. For an infinite dimensional lens space with fundamental group Z3, then say two people can aggregate. Okay, so it's not always that two people can't get together and that you need to have a majority, right? For voting, you always have the problem if there are two people, then you don't get a majority. But if you have three people, you get a majority. That's not really the source of this phenomenon.
Shmuel, if the space X is highly connected, can you get partial results? Like, if it's n connected, then maybe, n minus one people can average or something like this?
No. This is saying that if you have a space X, and so you have any number of people, if X is not contractible, okay, yeah, so, I'm going, so let me, I'm going to change the direction in which I'm going, okay, but.
Sounds good. Perfect.
But that's okay, because, because it happens to be that I love all directions equally, and you as a voter should have a say in this talk, okay? So this theorem is this: if I take a finite complex and it's not, say S92, okay, then for no value of n other than 1 can I do aggregation.
Uh-huh.
Okay, I can't do it with 2 people or 3 people or 4 people. By the way, 2 implies 4, because otherwise I would just give each person 2 votes, right? So there's some connections among these things, but it turns out that all of those things are completely irrelevant. Interestingly enough, okay?
Mm-hmm. Thanks.
Okay. Okay. Yeah. So. Okay. Now, there's a way of motivating what goes. So, by the way, so what do we do when you have a theorem like this? That these kind of things are never possible when you don't have some kind of version of convexity, right? You don't have contractibility. So, one thing that you could do is you could, take your X. And so there are, so here are 2 kinds of solutions. I mean, the point is to take X and embed it in something contractible. If you could, motivate it. Okay. So one kind of thing is I could always take any x and include it in the cone. This is something that in practice people do more often than they realize. Okay, this extra direction is like a real number, and what you could think of it as being some kind of payment. Okay, but you do it, right? I mean, you bribe people. You say, oh well, you wanted this point x. We're going to do something else, and then we'll include some compensation. Okay, so that and that maybe this point here really is infinity, right? I mean, of course, you very rarely, in the situations where in practice somebody would have to get an infinite payment, they probably don't in fact pay him off. But this is one kind of idea. Another kind of idea that people sometimes will do in situations like this. This goes in the literature. It's sometimes referred to as Solomonic judgments, because where you can't divide things up. Well, what you do is you could embed x as being the Dirac measures inside the space of. Okay, and now you say, well, aggregate and get a measure that's, and then once I have a measure, then it will be by sampling randomly using the measure. And of course, this is a perfectly good thing to do. You can imagine doing this at a department meeting. Instead of taking votes, you just spin a roulette wheel, and whichever person in the department's opinion gets picked is the one who's picked, and that's evidently fair. And of course, if there are a lot of people who agree with that person, there's a good, the most like, if you have a not too divided department, there'll be a whole faction that's happy with that. And this faction that contains a third of the department, they'll get their opinion followed a third of the time. Not so terrible, but it's definitely a solution that you might not think about a priori, but that does come up, immediately by doing, the standard tricks. Oh, how do I include a space into a contractible space that reflects some of the geometry? Let me talk about very, very briefly sort of a pessimistic implication. I'm really sorry. I hope to make everything a bit more quantitative, but I've only discussed the qualitative side of things. But that's, my own inefficiency. And then, possible occasional solutions. Okay, so here's one kind of, so this kind of solution occurs also in the economics literature when people were responding to the arrow paradox. They were saying, oh, well, that's because Arrow was imagining that there are voters who would have any possible ordering, of the candidates. But in fact, people care about specific things, so not all possibilities will really occur. Okay? So another possibility is this. I have this x, and I'm trying to aggregate from x to the n to x. Okay? I'm trying to find such a function, an a sub n. And here's a little theorem whose proof is much more trivial. It took me quite a while to find, but for quite a while I thought this was deeper than it is. But it's but nevertheless it's been true for quite a while, which is this: that for any x, say a polyhedron, a finite polyhedron, okay, typically what the technical condition compact A and R, positive epsilon, such that if d of xi, xj are all less than epsilon. So in other words, these guys, they all disagree with each other. Okay, they don't necessarily agree, but people are, more or less homogeneous. So this is, I call this pessimistic. This is sort of the nationalist solution. Okay, and the idea is that, well, if you have all these, then there exists, some a sub n, that will do this, for every n. And in fact, the a sub n of some vector, the distance between that and any of the xi's will still be less than epsilon. So if there aren't outliers, Okay, if you have a sufficiently homogeneous electorate, okay, right, and then you can do this. The only thing that's interesting here about the theorem, I mean, is the fact that it's the same epsilon. It's quite trivial to prove that there's an epsilon sub n that will do it. Okay, but the fact that you don't have to become more nationalistic, so to speak, you don't have to make epsilon go to 0 as n goes to infinity, that's sort of the only interesting thing in this theorem in its original form. But there's sort of a second partial solution that's even suggested by this one, which is this. So that's sort of the pessimistic implication that that this is a solution. But there's sort of another kind of possibility, which is a different way of getting contractibility, which is suppose that my voters, okay, I'm going to choose a different contractible space that contains X. Okay, suppose that the voters have to choose paths connecting, a given point X naught, for a time period, t going between 0 and 1. Okay, I'm not okay. So right. So in other words, okay, and right. So this space. Okay, so the path space. So let's just think about this. This is a space that algebraic topologists study all the time. Fair made us understand that even though this is a big, horrible, infinite dimensional space, it has a lot of useful algebraic topology properties. It's an infinite dimensional cousin of X. It's homotopy equivalent to X, but lots of times it does things better. And of course, in a lot of situations, the path space has its own meaning. And if I were giving a second lecture, I would, of course, say that paths might be induced through negotiation processes, right? That there are initial conditions, but then, my opinion will change as time goes on, as I see things implemented and I see what else is going on. And that lots of times, really what I should be choosing are not points, but I path space, okay? That has good news and bad news, which in terms of there are situations in which aggregation is possible via fiat, but the insistence that it would come via some kind of mediated mechanism, makes it harder. There are additional topological restrictions. But anyway, this thing here, but suppose, right? So now I want to, instead of my guys picking endpoints here, right? I'm going to insist that my voters not only tell me what they want, I want them to tell me how are they going to get there. Okay? Don't just tell me, now of course if it's a hiring decision, this doesn't work. But if it's a question about, I really want to, change society in some way. Okay? So then don't just tell me your conclusion. I want you to give me some process. Okay? So now the basic point is that for all n, so I'm going to call this the piece of X. Okay, so let me write down what this is. Okay, so this thing here is a set of n paths, gamma 1 through gamma n. These are all paths from 0, 1 into X. Okay, and the condition is that all the gamma 1 of 0 equals gamma 2 of 0 equals gamma n of 0. Right? Everyone, has their view about what it is we should do, a timetable, a plan. Okay? Okay? So that's what this sub X means. It means that they go to the same point within X. And then the statement is, for all n, there exists an aggregator that will go from piece of X to the n to, okay, is no big deal. But of course, what I mean is that the aggregated guy also starts at the same. Proof of this to a topologist is quite easy. It was before, which is, which is to, you have a contractible space. You see, each of these guys are a fiber of an actual map from here to here. So these things are all individually contractible. So the fact that you could combine them and aggregate, right, that was one of the exercises on an earlier blackboard. So this is a quite easy problem, but it's philosophically important. It says that when we have insoluble problems, then the point isn't to begin looking at our goals and stuff like that. It suggests that sometimes you can go ahead and aggregate by, just getting into the weeds. First, it has to be the case that even if we disagree about, you have to be able to agree about what's currently going on in the present. Okay, so that unfortunately is a hypothesis that I haven't questioned in earlier years. But on the other hand, it does say that, it gives you a different mechanism, not one based on randomness or anything like that for introducing this. My time is over, so I will stop. Okay.
Fantastic. Thank you
That's
much. Thank you so much, Shmuel. Are there any questions for Shmuel? You can go ahead and unmute yourself.
Yeah, it's Ira. Just a statement. Your Talmudic discussion, I believe the unanimous vote was only needed for a murder case, which brings me to the point of the voting strategies might change based on how important the thing is. In other words, if you're trying to decide which candy to put in the vending machine, people might have a different strategy than to pick who the next tenured professor is going to be, and that might change some of the mathematics, sort of give you a graded voting strategy.
Unfortunately, I only heard a portion of, of your question. Can you try again? Maybe I'll hear a different portion. And then I'll be
okay. I'll ignore the Talmud and just get right to the point. Depending on what the vote is, the voting strategy might change. In other words, one strategy might be for something minor. People might vote a certain way or not care, such as candy in a vending machine. But who's going to be the next person to get tenure? They might change their strategy, and the mathematics behind this might change as sort of a graded structure.
Absolutely. That was one of the points that I tried to make in the beginning, that there are many, many different kinds of aggregation problems. Right? I mean, there are the ones where you really are, let's say you're having a whole bunch of different trying to combine their opinions. And advisors, I guess they like being listened to, but really, you paid them for their advice. They gave you technical advice, and now you still have to go ahead and decide for yourself. You're the one who's making the decision, and you want to do the best thing. And then, you'll be doing it by various optimization methods and so on. This topological choice one is based entirely on a naive idea of what it would mean to be fair, which, just had, and I think has that, it has the unanimity, despite the Talmudic example, I think is a fine one. Democracy is, I think, like I said, people play around with that, and there are different versions of the theorem. It's a rationality one that I think might not be correct, which goes back to the example about people choosing candidates. The reason is that you could easily imagine, suppose that I did the following. I have two people, and what I would do, and I'm on a Riemannian manifold. So one reasonable method would be is I draw the geodesic from P to Q and I choose the midpoint. That will almost always work. Where won't it work? So like I'm on the two sphere, and then there are infinitely many geodesics that connect the North Pole to the South Pole. Okay, so if I pick, so if I have points approaching the North and South Poles, and I take the limit, those were all lying somewhere in the middle. But what happens at that pole, the place where it's independent, what really ends up happening is that, there's a whole circle's worth, namely the equator of geodesics, and if you chose the midpoint on any of them, continuity would cause a problem because it then depends on how you approach the North and South Pole. But the fact of the matter is that there are other choices that aren't optimal, You know, I mean, you don't really care which of those you choose along the equator. There isn't a principled method. And, you know, what might be, you know, so then it makes you realize you want to be building in rationality. You know, it's maybe not so bad to allow you to, maybe you really do want to have a measure, right? Where I have the optimal guy, but then I have the suboptimal guy, but they're not so suboptimal. And, you know, I'm willing to compensate them in some fashion. But I think, but I agree with it. I think your central point. So I guess so by the way, so another way in which this comes up is if you begin trying to implement these things via paths. Okay, so that, for example, I have two people, you know, rather than just say the way in which I'm going to get them to agree, I imagine I'm having some kind of negotiated solution and see how that would lead. So that, in other words, they both would, you know, that not only do I want to have a midpoint between them, I really want to imagine a process that produces it. You know, some set of negotiation taking place over time. So in that case, right, I mean, then I would be trying to be going from a pair of 2 points to a path between them that would have certain kinds of properties. Okay, I have that. I'm just introducing that model for a reason. It turns out that model occurs in robotics. This is Farber's topological complexity model in robotics. And again, the situation is that you can always do negotiation for two people in this way if and only if your space is contractible. But for that one, there's a very important quantitative aspect, which is, suppose that I am contractible. I can now ask, how long will the negotiations take? Okay, so I have an X, okay? I have some specific X. I'm going to call it F, name it after Farber. Okay, and F really is contractible. So there is a way of going from F cross F to paths of negotiation within F. Okay, but the question is, F is this nice compact space. Okay, so there's a theorem that these paths will exist or whatever. The trouble is that the question about whether a space is contractible or not turns out to be an undecidable problem. There are, if you look about finite three-dimensional complexes, there's no algorithm to decide in general if such a complex is contractible. So that means that there's no algorithm to decide whether there is such a concretely means. It means that even when there is such a function, it depends on how long you allow your paths to go. Are you going to allow your paths to wind in and around in complicated ways all over this? So what does that boil down to? How much resources are you willing to allocate to a decision process? Okay, so that was actually a direction that I had wanted to go, and that it turns out to connect to persistent homology and persistent homotopy theory, because as you go ahead and begin imposing costs to solutions to problems, right? And that was your point, that there are some trivial problems where you would do one thing, but for the non-trivial problems, there are more resources that you're willing to allocate to actually solving the problem and making it a really good solution. So then that introduces sort of some extra parameters, and that will make a difference where the geometry of the space, more so than just the topology, would enter, at least if you're modeling things in this way.
Okay.
Long-winded, didn't quite ask.
Thanks.
Satisfied anyway.
Shmuel, we have one question that David Snyder chatted in. So the question is, has this been typed up at all yet?
So part of it has and part of it hasn't. I have an old paper that appeared in the Journal of Economic Theory that explains the fact, the negative result about that you can't aggregate for a finite simply connected complex. And it turns out that theorem in economics was discussed earlier, was proved earlier by Ekman, Hilton, and Gadea. They were studying the question. They didn't call it aggregation. It was some old paper. It was sort of funny. I was completely unaware of the paper when I wrote mine and found out about it the day before I was supposed to give a colloquium about this at ETH. So I was lucky because Ekman was in the audience, but I had found out the day before. But anyway, so the stuff about, just plain aggregation and the Chichelnitsky model and things like that are in this paper, which you could find on my webpage. I mean, I only have one paper in Journal of Economic Theory. Sort of the idea of then going to path spaces and that aggregation then is possible, or when things are sufficiently nationalistic, I haven't yet written up. I have the feeling that those things are going to be preliminary. There's a connection between this stuff and topological robotics, part of which is indicated by like these paths, where things are getting to be more quantitative. And I suspect that this stuff that I talked about today isn't going to be written up anytime in the near future. I think it's going to be swallowed up in a later paper that will likely be seemingly about a different topic.
Fair enough. Yeah.
Okay.
Other questions for Shmuel? Well, if not, let's go ahead and unmute yourselves, and let's give a round of applause to thank Shmuel for the fantastic talk.